Welcome to SERVOsoft, size-complete servo systems. This tutorial showcases SERVOsoft's powerful slider crank mechanism. The slider crank model in SERVOsoft is a full dynamic model, considering the motion profile, inertia, mass, and gravity effects throughout the entire range of motion. This tutorial will demonstrate a vertical slider crank stamping press used to punch sheet metal. The project is already loaded with the mechanism data, so now I will go to the mechanism data. First, I want to explain the orientation of the mechanism. The incline angle increases in the counterclockwise direction. If the incline angle is greater than 0, the load is above the crank pin. If the incline angle is less than 0, the load is below the crank pin. Therefore, for a vertical press, the incline angle is minus 90 degrees, since it will use gravity to help in punching down on the sheet metal. Note that the slider crank allows for an incline angle between minus 180 degrees and positive 180 degrees. The crank length is 100 millimeters and the connecting rod is 500 millimeters. It is important to note the center of mass for the crank and the connecting rod. In this case, they are half the length of the crank and connecting rod, which is 50 and 250 millimeters respectively. The rest of the inputs here are inertias and masses, and are straightforward. Now the load parameters are shown, where we have a load mass of 100 kilograms. Here we can select where the motion profile is defined and its start position. The motion profile can be specified at the crank as a rotary profile and the start position as an angle. Or, the motion profile can be defined at the load as a linear profile, and the start position is a linear position within the valid range for the mechanism. When defining the profile at the load, the Maintain Crank Turning Direction option is also enabled. Because of the geometry of our mechanism, the linear position range is limited to the fully retracted and extended positions, which in this case is between 400 and 600 millimeters. Note that the linear position is defined from the crank pin. For this application, I will select the motion profile at the crank, which is a rotary motion profile. The start position is 180 degrees, which places the load in the up position at the start of the sequence. I will click OK to accept these inputs. And next, I will create the motion sequence. The sequence will have 3 segments. The press completes 1 cycle every second, and the press is in contact with the material from 165 to 195 degrees, where 180 degrees is the fully extended position. I will name the first segment down. The distance traveled is 165 degrees, and it is a constant velocity segment at 360 degrees per second. Next, I will create the second segment called punch. The distance is 30 degrees, which is the press contact window with the sheet metal from 165 degrees to 195 degrees. The constant velocity is 360 degrees per second. During this segment, there is also a cutting thrust force of 1000 newtons as the press cuts the sheet metal. So we apply this thrust force under the payload thrust tab. I will name the final segment up. The distance traveled is 165 degrees, and it is a constant velocity segment at 360 degrees per second. Now let's examine the sequence. The default profiles, load position, and load velocity are shown in the chart. We see the rotary motion profiles listed in the data table. This is because we chose to define our motion profile as a rotary profile at the crank. Had I chosen to specify a linear profile at the load, the data table would show linear data. I'll add the crank position and velocity profiles in a second chart to demonstrate. And then enable profiles 3 and 4 and select the gearbox stage, since the gearbox output is at the crank input. I will select distance for profile 3, which is the crank angle distance, and profile 4 is the crank velocity. Now we see a constant rotary velocity of 360 degrees per second at the crank, and the gearbox output angle, which is also the crank angle, ranges from 180 degrees to 540 degrees over the 1 second cycle. Recall that the 180 degrees start angle was defined earlier in the mechanism data. To visualize what is going on, I will click the chart crosshairs, and the crank mechanism will be displayed to help visualize its orientation. To examine our sequence even further, let's look at the thrust load and crank input torque by adding 2 or more profiles to the chart. So as the press enters the contact window with the sheet metal, the 1000 Newton thrust load is added. The punch press moving mass is 100 kilograms, so with gravity, this is almost identical to the required punch force of 1000 newtons. Hence the crank torque is relatively small during the punch segment. Now we can take this one step further by simplifying the sequence from 3 segments down to 1, but achieving the exact same results with a thrust force. I will append one constant velocity segment, rotating 360 degrees in 1 second. Then I will use the thrust formula to apply the 1000 Newton thrust between 165 and 195 degrees. As you can see, the 4th segment using the thrust formula is identical to the first 3 segments. This concludes the SERVOsoft tutorial on the slider crank mechanism. Thank you.